New optical method reveals internal dynamics of elusive Wigner crystals. By University of Basel. Edited by Sadie Harley, reviewed by Robert Egan. Editor's notes. The gist. Add as preferred source. Optical signatures of a Wigner crystal in a WSE2 monolayer. Credit, Lujunwang et al. Researchers at the University of Basel and the Technical University of Munich have developed a new method to reveal the collective motion of electrons in one of the most elusive states of matter, the Wigner crystal. Using light, the physicists were able to uncover previously inaccessible properties of this fragile quantum state. When electrons confined to a two-dimensional plane interact strongly with one another, they can stop moving independently and instead form a periodic lattice resembling the atomic arrangement in an ordinary crystal. This ordered state, known as a Wigner crystal, has fascinated scientists for decades because its order does not arise from the internal structure of the host material, but from interactions among the electrons themselves. Although Wigner crystals have been observed in several physical systems, probing their internal behavior, how they move, interact, and respond to external perturbations has remained a major challenge. In a study published in Nature Physics, a team of experimentalists led by Professor Tomasz Smolenski at the University of Basel investigated a single atomic layer of tungsten diselenide cooled to just a few degrees above absolute zero. By illuminating the material and measuring the reflected light, the researchers observed new optical features that reveal the collective behavior of electrons within a Wigner crystal. Light reveals hidden quantum behavior. These features arise from a subtle interplay between light-generated excitations in the material, known as excitons, and the ordered arrangement of electrons. The resulting hybrid quasi-particles, called Wigner crystal polarons, act as highly sensitive optical probes of the crystal and its collective dynamics. Our measurements show that light can do more than simply detect the presence of this exotic state. It can reveal how the state behaves internally, says first author Dr. Lujunwang from the University of Basel, who carried out the experiments together with Ferdinand Menzel, a PhD student in Smolenski's group. This gives us a powerful new tool for studying collective excitations of electronic crystals that would otherwise be extremely difficult to access, adds Smolensky. The researchers also found that the strength of the interactions among the electrons shapes these optical signatures. This makes them particularly valuable for exploring the fundamental physics of strongly correlated systems, whose properties arise from the collective behavior of many interacting particles. To explain the experimental results, theorists led by Professor Michael Knapp at the Technical University of Munich developed a theoretical description of how Wigner crystal polarons emerge from the coupling between optically generated excitons and the collective motion of electrons in the crystal. A new window into strongly interacting materials. What is particularly exciting is that these signals carry information not only about how the electrons are arranged, but also about their quantum dynamics, explains Fabian Pickler, a PhD student at TUM. This allows us to connect the experimental observations directly to the underlying many-body physics. The results show that atomically thin materials offer a promising platform for visualizing the collective motion of electrons in ordered quantum states. This opens up new possibilities for gaining a better understanding of the internal dynamics of strongly correlated matter.